When we multiply two complex numbers, we get a new rotated and scaled complex number as compared to the original two numbers. Here I am using vectors to represent points on the complex plane. This light blue colored vector represents the product of the other two. Now, why is this true? That is, why does multiplication have the effect of scaling and rotating in the complex plane? First, let's take a look at this. We know that any vector can be split into its subcomponents, that is, the horizontal and the vertical components, or in our case, the real part and the imaginary part. These are by definition perpendicular to each other. Their magnitudes are determined by how much the resultant vector is rotated from the horizontal, or in our case, the real number line. We will let theta represent the angle rotated and r as the magnitude of the main vector. As you know, complex numbers give us I, the square root of -1. You must have heard that multiplying a number by I has the effect of rotating it by 90 degrees in the complex plane. This is because when multiplying by I, the real part of the number is flipped counterclockwise to the imaginary line, and similarly, the imaginary part is flipped counterclockwise to the real number line, as I times I, or I squared, is equal to -1. Moving on, here is some arbitrary point t, equal to a plus bi on the complex plane. We need to rotate this point by some angle alpha, as shown here, to point q, equal to c plus di. For now, this is just a rotation, so q and t are both of the same magnitude. What should we multiply t by to get to q? Well, remembering that vectors can be split into their subcomponents, here's one thing we can do. Duplicate t vector and scale one of the duplicates by cosine of alpha. To the other duplicate, multiply it by I and then scale it by sine of alpha. Multiplying by I has the effect of rotating it by 90 degrees. Adding these two duplicates together, we can see that we have successfully transformed point t to point q. What we just did is transform t to the subcomponents of q, and thus adding these subcomponents gave us the point q. To make it more clear, let's change the perspective a little. You may rotate the graph such that our original vector representing point t appears to be the base of point q. You may now repeat the process mentioned previously. Note that the values of t and q will of course still be a plus bi and c plus di. This is just a change of perspective. When you rotate everything back to normal, you can see that we have successfully transformed t to q. In terms of algebra, we can see that we multiplied point t by cosine of alpha plus I times sine of alpha. This implies that any point x can be rotated by some alpha degrees simply by multiplying by cosine of alpha plus I times sine of alpha in the complex plane. One last thing, we know that cosine of theta plus I times sine of theta, where theta is the angle made with the real number line, just represents the unit vector. That is, the set of all points with magnitude 1. This is extremely important, as all points in the complex plane are just a scaled form of this unit vector. That is, any point A can be represented as cosine of theta plus I times sine of theta times the magnitude of A, where theta is the angle point A makes with the real number line. So finally, when you're multiplying two complex numbers, A and B of different magnitudes and of angles alpha and beta respectively, they can be broken down like this. Magnitude of A times cosine of alpha plus I times sine of alpha times magnitude of B times cosine of beta plus I times sine of beta. What that means is that a unit vector of angle alpha is rotated by angle beta, or vice versa, and then scaled to the products of the magnitudes of A and B. and therefore, when two complex numbers are multiplied, the new value formed is said to be a scaled and rotated version of them. Complex numbers are extremely useful. They are used in many fields ranging from quantum physics to computer science. They are also very helpful in computer graphics. In fact, in this video, the animation of vectors and graphs were made with the help of complex numbers. Before you go, here's a fun little exercise that you should try by yourself. Using what you learned in this video, try to prove the angle sum property of sine and cosine using complex numbers. Thank you very much for watching. I hope you found this video helpful.